Tonight, we're going to imagine something that physics says is impossible, and then we're going to use it anyway. Imagine that we cracked it. Imagine that every barrier fell away, every engineering limit, every problem with fuel and mass and energy, and we built a ship that could travel at the speed of light. The fastest thing the universe allows. Nothing in all of existence moves quicker than this. It is the hard ceiling written into the laws of reality, the one number that nothing, anywhere, has ever beaten. Even at that speed, even moving as fast as the universe will permit anything to move, it still won't be enough. Not even close. By the end of tonight, you're going to understand exactly why the cosmos is built on a scale so vast that the ultimate speed limit feels almost like standing still. And why some places in the universe are not just far away, but permanently, eternally out of reach, no matter what we invent. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with the speed itself, because to feel the disappointment that's coming, you first have to feel the thrill. Light moves at 186,282 miles per second. In a single tick of a clock, a beam of light crosses a distance greater than 7 times around the entire planet. In terms of speed per hour, light travels about 670 million miles every hour. These are numbers that don't fit into anything you've ever experienced. A bullet leaves a high-powered rifle at around 2,000 miles per hour. A jet fighter, at full afterburner, might reach about 1,500 miles per hour. The fastest spacecraft humanity has ever built, the Parker Solar Probe, screams through space at around 430,000 miles per hour when it whips past the sun. That probe is the fastest object human hands have ever made. And light is still more than 1,500 times faster than that. So when you imagine a ship that moves at light speed, you are imagining the absolute pinnacle of what motion can be. There is no faster. This is the top, and it should feel like cheating. It should feel like the universe has been conquered. For a little while, it almost is. Before we go anywhere, it's worth pausing on how we even know the speed of light, because the story is one of the quiet triumphs of human cleverness. For most of history, people assumed light was instantaneous. You light a candle, and the room is lit at once. There seemed to be no delay, no travel time, nothing to measure. The great thinkers argued about it for centuries without resolution. Some insisted light moved infinitely fast. Others suspected it had a speed, but had no way to test the idea. The breakthrough came in 1676 from a Danish astronomer named Ole Rømer. He wasn't even trying to measure the speed of light. He was studying the moons of Jupiter, specifically the innermost large moon, Io, which dips behind the giant planet and reappears on a precise schedule. Rømer noticed something strange. When the Earth was on the side of its orbit closest to Jupiter, the eclipses of Io happened slightly earlier than expected. When the Earth was on the far side of its orbit, the eclipses happened slightly later. He realized what this meant. The light carrying the image of Io's reappearance had farther to travel when the Earth was farther away. The delay wasn't a change in the moon's orbit. It was the time it took light to cross the extra distance. From this, Rømer made the first real estimate of the speed of light. His number wasn't perfect, but it was the right order of magnitude, and far more importantly, it proved something profound. Light has a speed. It is fast, but it is finite. It takes time to get from one place to another. That single insight changed everything, because it meant that looking out into space was the same as looking back in time. Over the following centuries, the measurements grew sharper. In the 1800s, scientists like Hippolyte Fizeau and Léon Foucault devised clever experiments using spinning-toothed wheels and rotating mirrors to clock light over distances here on Earth. They sent beams across miles of open air and timed them with mechanical precision that seems almost unbelievable for the era. Later, Albert Michelson refined the technique to extraordinary accuracy, bouncing light between mountaintops and measuring the tiny time it took to return. Each generation pushed the number closer to what we know today. And what we know today is exact, because the speed of light is now built into the very definition of distance. The meter is defined by how far light travels in a precise fraction of a second. The speed of light isn't just something we measure anymore. It's the ruler against which all distance is set. That's how fundamental this one number is. It is woven into the foundation of physics itself. There's a deeper question lurking here, and it's worth sitting with for a moment. Why does light have a speed limit at all? And why that particular speed? When we say the speed of light, we're really talking about something far more fundamental than light. We're talking about the speed of cause and effect itself. Light just happens to travel at that speed, because light has no mass, and anything with no mass travels at the maximum the universe permits. But the limit isn't really about light. It's about how fast any influence, any signal, any piece of information can pass from one place to another. If you flick a switch here, the effect of that action, the ripple of cause spreading outward, cannot reach a distant place faster than this speed. It is the rate at which the universe updates itself. It is the speed of this caused that. That's why nothing can beat it. If something could travel faster than light, it could, in a sense, arrive before it left. And cause could come after effect. The orderly flow of events that makes reality make sense would unravel. So the speed limit isn't an inconvenience the universe imposes on us out of spite. It's the very thing that keeps cause before effect, that keeps the story of the universe in a sensible order. Light is simply the messenger that travels at this ultimate pace, carrying the news of every event outward across space, never faster, never slower. And light is a strange messenger. It has no mass, no weight, nothing you could hold. It is pure energy, woven from electric and magnetic fields that take turns creating each other as they ripple through empty space. Visible light is only a thin slice of a far broader spectrum. The same kind of waves, traveling at the same speed, include radio waves and microwaves at one end, and ultraviolet, X-rays, and gamma rays at the other. All of them move at exactly this one speed. When we look out into the universe, we're catching these waves as they arrive, decoding the messages they carry from across unfathomable distances. But every message takes time to arrive. And that simple fact, that light is fast but finite, is what's about to make our journey so humbling. Now picture yourself on board this ship, looking down at Earth, ready to leave. You fire the engines, and instantly you are moving at the speed of light. The moon is the first thing you'll pass. It sits about 239,000 miles from Earth, on average. At your speed, you reach it in just over 1.25 seconds. You blink, and the moon is behind you. The same trip that took the Apollo astronauts 3 full days, you've just done in less time than it takes to clear your throat. Already, this feels miraculous. Next comes the sun. Our star sits about 93 million miles away. That sounds enormous, and by human standards it is. But at light speed, you cross that entire gulf in about 8 minutes and 20 seconds. Think about what that means. The sunlight, warming your face on a summer afternoon, left the sun's surface more than 8 minutes ago. If the sun were to suddenly vanish, you wouldn't know for 8 minutes. The Earth would keep orbiting an empty space, bathed in light from a star that was already gone. That is the reach of light speed inside our own neighborhood. It makes the inner solar system feel almost small. Let's keep going outward. Mars, when it's on the far side of its orbit from us, sits around 250 million miles away. You'd reach it in around 22 minutes. Jupiter, the giant, lurks roughly 484 million miles from the Sun. Light from the Sun takes about 43 minutes to get there. Saturn, with its glorious rings, is around 890 million miles out, about 1 hour and 20 minutes at light speed. By the time you reach Neptune, the outermost true planet, you're nearly 2.8 billion miles from the Sun. Light takes about 4 hours and 10 minutes to travel that far. So, in a single afternoon, moving at the ultimate speed, you could cross the entire planetary system, from the Sun all the way past Neptune. Even on that afternoon, though, something would surprise you. Empty. That's what the journey would feel like. For all the wonder of the planets, the spaces between them are overwhelmingly empty. You'd leave the Sun, and for many minutes there would be nothing but black, until tiny Mercury slid by, then the bright crescent of Venus, then the blue marble of Earth and its small moon. Beyond Mars, you'd cross the asteroid belt, and despite how it's often pictured, you would almost certainly see nothing at all. The asteroids are real, hundreds of thousands of them, some quite large, but they're spread so thinly across such an enormous volume that the average distance between them is hundreds of thousands of miles. Spacecraft have flown through the belt many times, and the danger of striking anything is so small it's almost not worth considering. You could fly straight through and never glimpse a single rock. Then would come the long stretches between the giant planets, vast gulfs of darkness with Jupiter, Saturn, Uranus, and Neptune appearing as rare islands of color in an ocean of black. This is the first lesson the universe teaches about itself. Space is mostly space. It is named perfectly. Even our own solar system, the most crowded and familiar piece of the cosmos we know, is almost entirely emptiness, with a few small worlds scattered across it like lonely lighthouses. And if the solar system, held tight by the sun's gravity, is this empty, then the gulfs between the stars and between the galaxies are emptier still, by amounts that defy the imagination. The afternoon journey across the planets isn't really a tour of crowded sights. It's a passage through a great deal of nothing, punctuated by a handful of precious worlds. That emptiness is the canvas on which everything tonight is painted. It's why even the fastest speed imaginable spends almost all its time crossing the dark, with the destinations few and far between. This is where the illusion is at its strongest. This is the moment where it seems like light speed has tamed the cosmos. You've crossed the solar system in an afternoon. Surely, the stars can't be that much harder. Hold on to that feeling, because it's about to break. Beyond Neptune, the solar system doesn't simply end. There's a vast region of icy bodies called the Kuiper Belt, home to Pluto and countless other frozen worlds. This is a broad, flattened ring of ice and rock left over from the birth of the solar system, never quite gathered into a planet, drifting in the deep cold far beyond the last of the giants. Out here, the sun is no longer a warm disk in the sky. It's a brilliant point of light, blazing brighter than anything else around it, but giving almost no heat at all. And noon would look little different from a moonlit night back on Earth. Pluto is just one resident of this frozen ring, joined by other small worlds with names like Eris and Makemake and Haumea, each one a sphere of ice and rock circling the sun across centuries. Beyond that, the sun's influence stretches on through a thin scattering of comets, and then, far out, a great shell of frozen objects called the Oort cloud. This cloud is thought to begin thousands of times farther from the sun than the Earth is, and to stretch out to perhaps 1.5 light-years away. It isn't a flat ring like the Kuiper Belt. It's imagined as a vast spherical shell wrapped entirely around the solar system, a faint cocoon of perhaps trillions of icy bodies, each one drifting alone in the dark, so far apart that a comet out there might have millions of miles of empty space in every direction before its nearest neighbor. Every now and then, a gentle nudge from a passing star or the slow tug of the galaxy sends one of these frozen wanderers falling inward. And centuries later, it arrives in our skies as a comet, trailing its long, bright tail, a visitor from the very edge of the sun's domain. And here, for the first time, that word appears. Light years. Not light minutes, not light hours. Light years. The Oort cloud, still technically part of the sun's domain, still loosely bound to our star by gravity, is so far out that crossing it at light speed would take you well over a year. The little ship that crossed from the sun to Neptune in an afternoon would need more than a year just to leave the sun's frozen outer suburbs behind. And that's still home. That's still our own front yard. We haven't even started the real journey yet. This is the first hint that something is deeply wrong with our sense of scale. Inside the planets, light speed felt unstoppable. But the moment we step past the planets, into the true space between the stars, the same speed begins to falter. The distances stop being measured in minutes and hours. They start being measured in years. And they will never go back. This is the right moment to make sure we understand what a light year really is, because everything from here on out depends on it. A light year is not a measure of time, even though the word year is hiding inside it. It is a measure of distance. It is simply how far light travels in 1 year, moving at that staggering speed of 186,000 miles every second, never slowing, never stopping, for an entire year without pause. That distance comes out to nearly 6 trillion miles. 6 trillion miles in just 1 light year. We switch to this unit for a simple reason. Once you leave the solar system, measuring in miles becomes useless. The numbers grow so enormous, so crowded with zeros, that they stop meaning anything to the human mind. Saying, a star is 25 trillion miles away, tells you almost nothing. It's just a smear of digits. But saying it's a little over 4 light years away tells you something you can hold. It tells you that light, the fastest thing there is, needs 4 years to make the trip. The light year quietly carries the speed limit of the universe inside it. Every time you hear that a star is a certain number of light years away, you're really being told the minimum number of years it would take to get there, at the absolute fastest speed reality allows. So when we say the nearest star is more than 4 light years away, that's not just a distance. It's a warning. It's the universe telling you, in its own units, exactly how long even the fastest possible journey would take. And the deeper we go tonight, the larger those numbers grow, until the light year itself, 6 trillion miles at a stretch, starts to feel small. To understand why the stars are so impossibly far, you have to understand the emptiness between them. Inside the solar system, things are relatively close together, held in tight by the sun's gravity. The planets feel spread out, but compared to what comes next, they're practically huddled together for warmth. Between the stars, there is almost nothing. The space between us and the nearest star is not filled with anything you could land on or even see. It is emptiness on a scale that the human mind simply was not built to hold. Let me give you one image to carry through the rest of tonight. If you shrank the sun down to the size of a grain of sand and placed it on a table, the nearest star, also shrunk to a grain of sand, would not be across the table. It would not be across the room. It would sit around 4 miles away. 2 specks of sand, 4 miles apart, with absolutely nothing in between. That is the true emptiness of the galaxy. The stars are not crowded together like lights in a city. They are scattered like a few grains of dust thrown across an entire ocean. And our ship, moving at the fastest speed the universe permits, must cross every single inch of that emptiness, 1 second at a time. This is the part that breaks the illusion. Speed only helps when there is a reasonable amount of distance to cover. When the distance is this immense, even infinite speed would barely help, and we don't have infinite speed. We have the speed of light. And the speed of light, it turns out, is heartbreakingly slow against a backdrop this large. Now we come to the first true wall. The nearest star system to our Sun is called Alpha Centauri. It's actually 3 stars bound together by gravity. 2 of them, Alpha Centauri A and B, are sun-like stars orbiting each other. The third is a small, faint red dwarf called Proxima Centauri, and right now it sits slightly closer to us than the other 2. Proxima Centauri is 4.24 light-years away. Let that sink in. At the speed of light, the fastest anything can ever travel, it would take 4 years and 3 months to reach the nearest star. 4 years of nothing. 4 years crossing pure, empty darkness, with the sun shrinking behind you into just another point of light, and the destination star growing so slowly you'd barely notice the change from 1 month to the next. And here's a detail that makes it more poignant. We now know that Proxima Centauri has at least 1 planet orbiting in the zone where liquid water could exist. It's called Proxima b, a world, possibly rocky, possibly with some kind of surface, circling the nearest star to our own. The closest, potentially habitable world we know of, our best first destination if we ever leave the solar system. And even that, the very nearest one, is more than 4 years away at light speed. Proxima Centauri is the close one. It's our next-door neighbor. If you wanted to visit Sirius, the brightest star in our night sky, you'd travel for about 8.5 years at light speed. To reach the bright blue-white star Vega, you'd need around 25 years. To reach Betelgeuse, the swollen red giant marking the shoulder of Orion, you'd travel for somewhere between 500 and 600 years. And remember, this is the maximum. This is not with current technology. This is with the best technology that physics will ever permit, the absolute fastest motion the universe allows. At that speed, a journey to a single nearby star is measured in years. A journey to a familiar star you can point to in the sky is measured in centuries. The thrill from the solar system is already fading. Light speed crossed the planets in an afternoon, and now it can barely manage a single star within a human lifetime. This is the pattern that's going to repeat again and again, getting worse every time. The faster we imagine going, the more we realize how staggeringly little it buys us. It helps to compare this with reality, just for a moment, because it makes the wall feel even higher. We have, in fact, sent ships toward the stars. Not on purpose, exactly, but we've launched probes that are now leaving the solar system entirely. The Voyager spacecraft, launched in the late 1970s, have been flying outward for almost half a century. They've passed all the planets, crossed the boundary where the sun's wind gives way to interstellar space, and they're still going, still faintly calling home across billions of miles. Voyager 1 is the most distant human-made object in existence. It travels at about 38,000 miles per hour. That is blisteringly fast by everyday standards, far faster than any car or plane. And yet, if Voyager 1 were aimed directly at the nearest star, which it isn't, it would take roughly 70,000 years to get there. 70,000 years for our fastest real probe to cross a gap that light crosses in just over 4. That is the chasm between what we can actually do and what we're imagining tonight. Our best real machine would need a span of time longer than all of recorded civilization, many times over, to reach the closest star. At light speed, you'd do it in 4 years. And even that, the absolute best the universe allows, still finds the galaxy almost impossibly large. So, when we talk about light speed not being enough, understand what that really means. It's not that we're being greedy. It's that the gap between the fastest speed in existence and the size of the cosmos is so enormous that even closing it completely barely helps at all. Let's take a slow look around our own stellar neighborhood, just the handful of stars closest to home, because even this tiny corner shows how lonely the geography really is. Within about 10 light years of the Sun, there are only a small number of star systems. You could count them on your fingers. Just beyond Alpha Centauri lies Barnard's star, a dim red dwarf about 6 light-years away, famous for slipping across our sky faster than any other star as it drifts through the neighborhood. A little farther out sit faint red dwarfs like Wolf 359 and Lalande, quiet, dim stars you'd never notice without a telescope, each one several years away at the speed of light. Then there's Sirius, the brightest star in our entire night sky, blazing white at about 8.5 light-years away. Sirius is actually 2 stars, a brilliant blue-white sun and a faint, dense white dwarf circling it, the burned-out core of a star that finished its life long ago. That white dwarf is roughly the size of Earth, yet it carries nearly the mass of our entire sun. A teaspoon of its material would weigh as much as a small car back home. Even the brightest, most familiar point of light in our sky turns out to hide a strange and crowded story. And it sits more than 8 years away at the only speed that can never be exceeded. A little past Sirius, you'd find the system called Luyten and the dim glow of Ross stars, faint red embers scattered through the dark. And here and there, tucked among these dwarfs, are the rare stars that genuinely resemble our own. Epsilon Eridani, a young orange sun, about 10.5 light-years away, circled by dusty rings and at least one giant planet, a system that looks a little like our own solar system might have appeared in its infancy. And Tau Ceti, a calm, sun-like star around 12 light-years out, long a favorite target for anyone dreaming of a second Earth, surrounded by a swarm of debris and possibly several planets of its own. These are the closest things we have to siblings of our Sun, and even they sit a full decade or more away at light speed, each one its own sealed world. unreachable in any human sense. And that's essentially the whole list within 10 light-years. A handful of stars, mostly faint, scattered through an immense volume of empty space. And to visit even the farthest of these closest neighbors at the speed of light would take the better part of a decade. To tour all of them, hopping from one to the next, would consume a human lifetime, and you'd have explored only the few stars nearest to home, while the galaxy's hundreds of billions of others stretched away, untouched, in every direction. This is the texture of the galaxy. Not a crowded city of stars within easy reach, but a vast, dark countryside, where each lonely homestead sits years of light apart from the next. And we hold the fastest speed there is, and still, the simple act of visiting our nearest neighbors would swallow a whole human life. There's one more strange detail about our immediate surroundings worth knowing. Our sun, and all these nearby stars, happen to sit inside a vast, nearly empty cavern carved out of the gas of the galaxy, a region astronomers call the local bubble. It's a pocket roughly 300 light-years across, where the normal thin haze of interstellar gas has been swept away, blown clear by the shockwaves of ancient stars that ended their lives in titanic explosions millions of years ago. We are, in a sense, drifting through the hollowed-out wake of long-vanished suns, riding through a bubble blown by deaths that happened before our species existed. And even this bubble, this relatively empty pocket of our galaxy, is so enormous that light itself needs 3 centuries just to cross it. The emptiness isn't an accident of where we happen to be looking. It's the fundamental condition of everything beyond our own front door. Before we go further out, we need to confront something strange. Something that, at first, sounds like a way out of this trap. When you travel close to the speed of light, time itself begins to behave differently. This is one of the deepest truths Albert Einstein gave us, and it changes the whole story. As you approach light speed, time for you, the traveler, slows down compared to everyone you left behind. This isn't a trick or an illusion or a matter of opinion. It has been measured countless times, with atomic clocks flown on aircraft and with particles accelerated in laboratories until they're moving at nearly the speed of light. The faster you move through space, the slower you move through time. At ordinary speeds, the effect is tiny, far too small to ever notice. But as you push toward the speed of light, it becomes enormous. For a beam of light itself, time essentially stops. If light could carry a clock, that clock would never tick. So, here's the seductive part. If you traveled to a star 40 light-years away at very close to the speed of light, an observer back on Earth would see your trip take about 40 years. But for you, inside the ship, far less time would pass. You might experience only a few years, or even less, depending on exactly how close to light speed you traveled. To you, the journey could feel short. For a fast enough ship, you could, in principle, cross thousands of light years within a single human lifetime, as measured by your own body and your own clock. This sounds like the escape hatch. This sounds like the universe quietly handing us a gift, a secret passage around the speed limit. But read the fine print, because it's brutal. While your personal clock runs slow, the universe outside does not wait for you. The Earth keeps turning. The years keep passing back home. If you fly to a star 40 light-years away and come back, then no matter how little you aged, at least 80 years will have passed on Earth. Everyone you knew when you left will be gone. Your family, your friends, the world you understood, all of it changed beyond recognition while you experienced only a brief trip. You would step off the ship, a young traveler, into a future where your own time had become history. Time dilation doesn't shrink the universe. It only lets a single traveler skip ahead, paying for the journey not in distance, but in everything and everyone they leave behind. You arrive young at a destination, but you can never truly go home, because home, as you knew it, no longer exists. The faster you go to beat the distance, the more deeply you're cut off from the time you came from. So even this gift, this loophole in the fabric of reality, turns out to be another kind of wall. The cosmos lets you trade away your connection to your own era in exchange for crossing its vastness. There's an even stranger consequence buried in this, one that quietly dissolves an idea we never even thought to question. We tend to assume there is a single, universal now, a present moment that's the same everywhere, stretching across the whole universe at once. You imagine that. Right now, as you sit here, something is also happening on a planet in Andromeda at this very same instant. But relativity tells us that now is not universal. There is no single present moment shared across the cosmos. Because light takes time to travel, and because time itself flows differently for observers moving at different speeds, the question of what is happening right now in a distant galaxy has no single, fixed answer. Two travelers passing each other at high speed would disagree about which distant events are happening simultaneously, and both would be correct. Space and time are not two separate things. They are woven together into a single fabric, which we call space-time. What you experience as the flow of time and what you experience as distance in space are two faces of the same underlying reality, and how they divide up depends on how you're moving through it. This means the universe is not a single ticking clock with everything happening in step. It's something far stranger. A vast web of events, connected by the threads of light traveling between them, with no master moment that binds them all together. When you look at a distant galaxy, you're not seeing it as it is now, because there is no shared now to see. You're seeing the light it sent, when it sent it, and that's the only honest way to talk about it at all. This is the universe we would actually travel through. Not a simple stage with a single clock, but a deep, interlocking fabric of space and time, where distance and duration blur into each other, and where the price of crossing space is always paid in time. And there's a harder limit underneath all of this, one we've been quietly ignoring. You can get close to light speed, but you can never actually reach it. This isn't an engineering problem we might solve someday. It's a fundamental feature of how the universe is built. The closer you get to the speed of light, the more energy it takes to go even a little faster. And the energy required to push something with mass all the way up to the speed of light isn't merely huge. It's infinite. A ship made of atoms, carrying people made of atoms, can approach the ceiling. It can get to 90%, 99%, 99.9%, but it can never touch it. Only things with no mass at all, like light itself, can travel at the speed of light. Everything else is forever locked just below. And the cost of climbing even close to that ceiling is almost beyond comprehension. To push a single ship up to near the speed of light would take an amount of energy comparable to everything our entire civilization produces over many years, poured into one vessel. Then you'd need that much again to slow down at the other end, because in space there's nothing to brake against. The faster you try to go, the steeper the cost climbs, rising without limit as you approach the speed of light. This is why even getting close, let alone reaching the ceiling itself, sits so far beyond us. It isn't a matter of building a better engine. It's a matter of energies that strain the resources of whole worlds. So, even this best possible journey, the fastest the universe allows, is bending the deepest rules of physics simply to exist. We're already cheating. And here is the punchline of tonight, stated plainly. Even when we cheat, even when we grant ourselves that ship and let it travel at the full, exact speed of light, the universe is still too big. The escape hatch is sealed. The loophole closes. Let me show you just how much too big it really is. We've been talking about single stars. Now, zoom out, far out, and look at the whole galaxy we live in. The Milky Way is a vast spiral of stars, gas, and dust, slowly turning in the dark. It contains somewhere between 100 billion and 400 billion stars. Nobody knows the exact number because we cannot count them all. We can only estimate by measuring the galaxy's mass and the light it gives off. And this galaxy is about 100,000 light-years across. Sit with that number for a moment. 100,000 light-years from one edge to the other. At the speed of light, the fastest motion the universe allows, crossing our own galaxy would take 100,000 years. Not a lifetime. Not a long career. 100,000 years. To put that into human terms, 100,000 years ago, our species had only just begun to look something like us. Modern humans were a small population in Africa, living in scattered groups, long before farming, long before cities, long before writing, long before any of the things we think of as history. If one of those early humans had set out at the very edge of the galaxy at light speed and started flying straight toward the other side, they still would not have arrived. The entire span of our species' existence is not long enough to cross the Milky Way at the speed of light. And we are not even near the edge of our galaxy. We sit about 25,000 light-years from the center, out in one of the spiral arms, in a quiet, ordinary stretch of cosmic suburb. To reach the supermassive black hole at the heart of our galaxy, an object called Sagittarius A, you would travel for 25,000 years at light speed. The center of our own galaxy, the place everything here orbits around, the gravitational anchor of our entire stellar neighborhood, is 25,000 years away at the maximum possible speed. And that center is a remarkable place. Sagittarius A is a black hole with the mass of around 4 million suns packed into a region smaller than our solar system. Around it, stars whip on tight orbits at millions of miles per hour, bent by gravity so intense that space itself is warped. We have even managed to capture an image of the glowing gas swirling around it, a faint ring of light circling a core of absolute darkness. It is one of the most extraordinary places in our galaxy. And at the ultimate speed, it lies 25,000 years from where you're sitting right now. This is the moment the scale truly turns over. In the solar system, light speed felt like power beyond imagining. Here, in our own home galaxy, it can barely crawl from one neighborhood to another within the lifespan of an entire civilization. And the Milky Way is just one galaxy. One among a number so large, we'll struggle to even say it. It's worth lingering inside our own galaxy a little longer, because even this single galaxy, which is just one speck in the larger cosmos, is a place of staggering richness. Imagine the journey across it at light speed, all 100,000 years of it, and think about what you would pass. In the first stretch, You'd move through the thin scattering of nearby stars, each one a sun, many with their own planets, their own possible worlds. Within just a few dozen light years of home sit hundreds of stars, and we now know that planets are not rare. Most stars have them. The galaxy likely holds hundreds of billions of planets, and a great many of those may be rocky worlds at the right distance from their star for liquid water. There could be 1 trillion habitable worlds scattered through the Milky Way, and almost every single one of them lies beyond any journey we could ever make. As you traveled on, you'd pass through vast clouds of gas and dust where new stars are being born. You'd cross regions like the Great Nebula in Orion, a glowing nursery where thousands of young stars are igniting out of collapsing gas, lighting up the cloud around them in soft, colored light. You'd pass towering columns of cold dust, light years tall, where gravity is slowly gathering material into new suns. You'd skirt the remnants of stars that have already ended, expanding shells of glowing gas thrown off in their final moments. The seeds of future generations of stars and planets scattered back into space. You'd move through the great spiral arms, where stars cluster more densely, and across the darker gaps between them. Our own sun lives in a modest spur of one of these arms, a minor feature sometimes called the Orion Arm, tucked between two of the galaxy's grander structures, the Sagittarius Arm, closer to the center, and the Perseus Arm farther out. We don't live on a main artery of the galaxy at all. We live on a quiet side street, a small bridge of stars between the bigger lanes, and even our humble spur stretches thousands of light years from end to end. As you crossed from one arm to the next, you'd pass through long stretches where the stars thinned out, the quiet country between the bright lanes, and then the density would build again as the next arm swept toward you. And high above and below the flat disk of the galaxy, scattered through the vast halo that surrounds it, you'd glimpse the globular clusters. These are ancient, tightly packed balls of hundreds of thousands of stars. Some of the oldest objects in the entire galaxy formed not long after the Milky Way itself began. Each one is a glittering swarm of suns crammed into a space just a few dozen light years across, frozen in place against the dark, orbiting the galaxy on long, looping paths that carry them far out of the disk and back again over hundreds of millions of years. And as you neared the center, the stars would crowd closer and closer together, the sky growing brighter, until you reached the dense central bulge and the brilliant, crowded core, with its supermassive black hole anchoring everything. All of this, every nebula, every cluster, every newborn sun, fits inside the single galaxy that light needs 100,000 years to cross. And when you finally reached the far edge and looked back, you would have seen only one galaxy out of 2 trillion. A single grain of sand, examined in detail, while an entire beach stretched away unseen in every direction. This is the scale problem in its purest form. Even the small parts of the universe are too large to know. Even one galaxy is a lifetime's journey at the speed of light, and there are more galaxies than there are grains of sand on all the beaches of Earth. And here's something that makes our place in this galaxy feel even more humbling. We are not sitting still. Our entire solar system, the Sun, and all its planets, is racing around the center of the Milky Way at roughly 500,000 miles per hour. We feel none of it. There's no wind, no sensation of speed, no sign at all that we're hurtling through the galaxy at that pace. And yet, even at 500,000 miles per hour, the galaxy is so vast that a single trip around its center takes about 230 million years. That span is sometimes called a galactic year. One lap of the Sun around the Milky Way. The last time the solar system was in this same position in its orbit, the earliest dinosaurs were just beginning to appear on Earth. Since the Sun first formed, it has completed only around 20 laps of the galaxy. 20 galactic years, across the entire history of our star. This is the quiet machinery of the cosmos. Everything is in motion, vast and slow and silent, on timescales that dwarf anything in human experience. We orbit a star. That star orbits the center of a galaxy. That galaxy drifts through a local group, which streams through a supercluster, which flows across the cosmic web. Layers of motion within motion, all of it carrying us along, all of it far too large and too slow for us to feel. And through all of it, the speed of light, the fastest thing there is, remains the same fixed limit, unchanged, indifferent, defining the edges of what any of this motion could ever reach. Here is where most people's sense of scale quietly gives up. The Milky Way is not alone. It is one member of a small cluster of galaxies called the Local Group, which contains more than 80 galaxies bound together by gravity. Most of them are small, faint dwarf galaxies, little smudges of stars orbiting their larger neighbors. But two of them are large. Ours, the Milky Way, and another great spiral called Andromeda. Andromeda is the nearest large galaxy to our own. You can actually see it with your naked eye on a clear, dark night, a faint, fuzzy patch of light in the constellation that shares its name. When you look at that smudge, you are looking at the most distant thing the human eye can see without any instruments at all. Everything else you see in the night sky, every individual star, lies within our own galaxy. But Andromeda is a whole separate galaxy, a city of stars in its own right, and it sits about 2.5 million light-years away. At the speed of light, reaching Andromeda would take 2.5 million years. That faint patch you can spot on a dark night is so far away that its light left it 2.5 million years ago. The light hitting your eye tonight began its journey before our species existed. When that light departed Andromeda, there were no humans on Earth at all, only our distant, early ancestors taking their first uncertain steps as toolmakers. You are, quite literally, seeing the deep past every time you glance at it. And if we aimed for Andromeda, traveling at the full speed of light, the journey would take longer than the entire history of the human story so far. There's a strange wrinkle to this one, though. Andromeda is actually moving toward us. In a few billion years, it will collide and merge with the Milky Way, the two great spirals slowly dancing together into a single, larger galaxy. This merger is one of the few cosmic events we can predict in detail, and it's worth picturing because it shows how strange these scales are even when galaxies do meet. You might imagine a collision as something violent, stars smashing into stars, a great cosmic wreck. But the stars within a galaxy are so far apart, separated by those 4-mile gaps in our grain of sand picture, that when two galaxies pass through each other, almost no stars ever actually touch. The galaxies glide through one another like two clouds of smoke merging, their stars threading past each other across light-years of empty space. Over hundreds of millions of years, gravity will slowly draw the two together, fling long streamers of stars out into the dark, and eventually settle them into a single, larger galaxy. If anyone is here to witness it, the night sky will transform. Andromeda, now a faint smudge, will swell over the ages into a great glowing band of light, stretching across the heavens, slowly twisting as the two galaxies entwine. It will be one of the most spectacular sights any sky could offer. But here's the point that matters for tonight. Even this, the nearest large galaxy actively falling toward us, drawn in by gravity over billions of years, is still so far away that its light takes 2.5 million years to reach us. The closest galaxy is coming to us, and it's still impossibly distant. That tells you everything about the gulfs between galaxies. When the nearest neighbor is on a collision course, and it still takes millions of years for its light to arrive, distance has become something almost beyond meaning. The local group itself, this little family of galaxies, is roughly 10 million light-years across. 10 million years at light speed just to cross our own immediate cluster of galaxies. And this cluster is, on the cosmic scale, tiny. It's a small town in a country we've barely begun to map. There's something the light from all these distant places carries with it, a quiet strangeness that's easy to miss. Because light takes so long to cross these distances, everything we see in deep space is a portrait of the past. We never see the universe as it is. We only ever see it as it was. Look at the famous cluster of stars called the Pleiades, the little knot of blue lights riding on the shoulder of the constellation Taurus. That light left those stars around 440 years ago. You're seeing them as they were centuries before you were born. Look at the Crab Nebula, the tangled, glowing wreckage of a star that ended its life in a tremendous explosion. We see that explosion's aftermath because the light has been traveling to us for thousands of years. In fact, astronomers nearly 1,000 years ago, in the year 1054, recorded a brilliant new star appearing suddenly in the sky, bright enough to see in daylight, before slowly fading. That was the explosion itself, its light finally arriving after crossing the void. What we see today is the slowly expanding cloud it left behind, still racing outward, still glowing. And here is the unsettling part. For the most distant objects, we genuinely do not know what they look like now. We see the towering pillars of gas and dust where stars are being born, light years tall, beautiful and serene. But that image is thousands of years old, and it's entirely possible that the real pillars have already been swept away by the blast of a nearby exploding star, gone for thousands of years, while we still gaze peacefully at their portrait in the sky. We are always looking at ghosts. Every star, every nebula, every galaxy, shown to us not as it is, but as it once was, the light still faithfully arriving long after the moment it captured has passed. The farther we look, the deeper into the past we see. And our journey would only make this stranger. Travel toward a galaxy 1,000,000 light-years away, and you're chasing an image 1,000,000 years old, trying to reach a place you can only ever see in its distant past, never knowing what truly waits there until you finally arrive. The universe doesn't just keep its distances from us. It keeps its present from us too. All we are ever given is the past, written in light, arriving late. Step back further, and the local group turns out to be part of something much larger. Our little cluster is one member of a vast collection of galaxy groups and clusters, all flowing through space together. Nearby sits the Virgo cluster, a dense swarm of well over 1,000 galaxies, anchoring an even greater structure called the Virgo supercluster. This supercluster spans about 110 million light-years. And even the Virgo supercluster, that enormous structure, turns out to be just one lobe of something bigger still. In the last decade or so, astronomers mapped the motions of galaxies across this entire region of space. They tracked how thousands of galaxies are slowly drifting, and they noticed that all of them, including us, are being drawn in the same general direction, toward a distant gravitational basin. By following these flows, they redrew the map of our cosmic home and discovered that we belong to a single connected structure far larger than anyone had realized. They named it Laniakea. The name comes from Hawaiian words, meaning immense heaven, and it is well chosen. Laniakea stretches roughly 520 million light-years across. It contains the mass of about 100,000 trillion suns. It holds tens of thousands of galaxies, all gently flowing toward a great gravitational center known as the Great Attractor. At the speed of light, crossing Laniakea would take 520 million years. The last time the Earth was that young, in terms of years gone by, complex animal life was only just beginning to flourish in the oceans. The journey across our home supercluster, at the maximum speed the universe allows, would outlast the entire age of complex animal life on our planet so far. And Laniakea is still not the universe. It is one structure among countless others. The cosmos is filled with superclusters, separated by enormous, nearly empty voids, arranged in a vast pattern that astronomers call the cosmic web. Galaxies gather along immense filaments and walls, threads of light strung across the dark, with great hollow voids in between, where almost nothing exists at all. If you could pull far enough back to see it, the universe would look like a tangled web of glowing strands, or the branching pattern of nerve cells, or the foam on the surface of the sea. We are a single droplet of light, clinging to one thread of that web. And even within this grand structure, we are being pulled. Our whole galaxy, our whole local group, is drifting at hundreds of thousands of miles per hour toward that distant gravitational center, the Great Attractor, buried deep within Laniakea. For decades, it was mysterious, partly hidden behind the dense band of our own Milky Way, which blocks our view in that direction. We could feel its pull in the motions of galaxies long before we could clearly see what was causing it. It turns out to be an enormous concentration of mass, a great convergence of galaxy clusters, drawing everything around it inward. And yet, here is the now familiar refrain. Even as we fall toward it, the Great Attractor lies so far away, and the universe is expanding so steadily that we will never arrive. We are drawn toward a destination we can never reach, across a distance that grows even as we fall. Between these great gatherings of galaxies lie the voids, and the voids may be the most staggering feature of all. These are vast, nearly empty bubbles of space, some of them hundreds of millions of light-years across, containing almost no galaxies at all. If you were placed in the middle of one of the great cosmic voids, the nearest galaxy might be so far away that the sky would look utterly black, with nothing visible to the naked eye in any direction. A creature evolving in such a place might believe its galaxy was entirely alone, floating in an infinite emptiness, with no hint that the universe beyond was full of light. Most of the volume of the universe is made of these voids. The bright filaments and clusters, the galaxies and superclusters, all of it is just the thin, glowing froth around enormous bubbles of nothing. The cosmos is far more empty than it is full, and the emptiness is on a scale that dwarfs even the galaxies threaded through it. So the picture sharpens into something almost overwhelming. We sit on one small world, orbiting one ordinary star, in one arm of one galaxy, drifting in one small group, on one thread of a web that is mostly empty space. being pulled toward a center we can never reach, inside a universe that is forever carrying most of itself away from us. And we are beginning, slowly, to grasp the shape of something so large that the word large itself stops carrying any meaning. Now, we arrive at the full picture. The observable universe, the entire region of space we can possibly see, stretches about 93 billion light-years across. You might expect that number to be about 27 billion, since the universe is around 13.8 billion years old, and light has only had that long to travel toward us. But the answer is far larger, and the reason is one of the strangest facts in all of science. Space itself is expanding. The universe is not a fixed stage on which galaxies sit still. Space is stretching, growing, carrying galaxies apart from one another everywhere, all at once. The galaxies aren't so much flying through space away from us as the space between them is swelling. Picture dots drawn on the surface of a balloon as it's being inflated. As the balloon grows, every dot moves away from every other dot. Not because the dots are crawling across the rubber, but because the rubber itself is stretching. That is what space is doing, in 3 dimensions, to the entire universe. We didn't always know this. For most of history, people assumed the universe was static, fixed, eternal, the same yesterday as it would be forever. The discovery that it's expanding is one of the great turning points in human understanding, and it came from carefully reading the colors of light. In the 1920s, the astronomer Edwin Hubble was studying distant smudges of light that many still thought were clouds of gas within our own galaxy. He proved they were galaxies of their own, vast islands of stars far beyond the Milky Way, and the universe suddenly became enormously larger than anyone had imagined. But he found something even more startling. When he measured the light from those distant galaxies, he noticed it was shifted toward the red end of the spectrum. Light from a galaxy moving away from us gets stretched to longer, redder wavelengths. In much the same way, the sound of a passing siren drops in pitch as it speeds away. The farther away a galaxy was, the more its light was shifted toward red, and the faster it appeared to be receding. Hubble had stumbled onto the fingerprint of cosmic expansion. Galaxies weren't just sitting still. They were all rushing apart, and the most distant ones were rushing fastest of all. This simple, profound relationship, that more distant galaxies recede more quickly, told us that the entire universe is growing. And if you run the expansion backward in your mind, rewinding the film, everything draws closer and closer together, until it all converges to a single, unimaginably hot and dense beginning. That insight gave us the age of the universe, around 13.8 billion years, and the picture of a cosmos that began small and hot and has been expanding and cooling ever since. So when we say the universe is expanding, this isn't a guess or a theory floating free of evidence. It's written in the stretched and reddened light of billions of galaxies, the same light arriving at our telescopes every night, every one of them carrying the same message. We are all flying apart. This is why the observable universe is so much wider than its age in light years would suggest. The light from the most distant objects we can see left them long ago, but in the time since, the space between us and those objects has stretched enormously, carrying them far, far farther away than they were when their light first departed. So the edge of what we can see now sits about 46 billion light-years away in every direction. That gives a full diameter of about 93 billion light-years. And within that vast bubble lie an estimated 2 trillion galaxies. 2 trillion. Each one a Milky Way of its own, give or take, holding tens or hundreds of billions of stars. If you tried to visit each galaxy and spent only a single second looking at each one, you would need tens of thousands of years just to glance at them all, and you would never have moved an inch toward any of them. At the speed of light, crossing the observable universe would take tens of billions of years. But here's the cruel part, the part that turns this from a story about distance into a story about loss. The expansion of space changes everything about whether we can ever reach these places, and it changes it for the worse. Let's understand exactly what cosmic expansion does to our journey, because this is the heart of tonight. Imagine you set out from Earth at the full speed of light, heading toward a distant galaxy. While you travel, the space between you and that galaxy is also stretching. For nearby galaxies, your speed is far greater than the rate at which the space between you is growing, so you gain on them and eventually arrive. But the farther away a galaxy is, the more space lies between you and it, and the more total stretching happens along the whole length of your journey. Beyond a certain distance, something remarkable occurs. The space between you and a distant galaxy stretches so fast, adds up so much, that the galaxy is effectively receding from you faster than light, not because it's moving through space quickly, but because there's simply so much space between you and it, and all of that space is growing at once. Now, nothing can move through space faster than light. That rule is ironclad. But space itself has no such speed limit. The expansion can carry distant galaxies away from us faster than any beam of light could ever close the gap. And this means there are galaxies in the universe right now, galaxies we can see, galaxies whose light is reaching us at this very moment that we could never reach. Not by any ship, not at the full speed of light. Not ever. Because no matter how fast we chase them, the space in between is growing faster than we can cross it. It's like trying to walk up an escalator that's moving down faster than you can climb. You can move as fast as your legs will carry you, and you will still be carried backward. This is perhaps the most humbling fact in all of cosmology. The universe is not just vast. Large parts of it are actively, permanently fleeing from us, slipping beyond reach with every passing moment, while we watch, helpless, holding the fastest speed in existence in our hands and finding it useless. Astronomers have a name for the boundary that separates what we can still reach from what we can never reach. It's called the cosmic event horizon, and it's a different thing from the edge of the observable universe. We can see far more than we can ever touch. The observable universe, 93 billion light-years across, is everything whose light has ever managed to reach us. But the reachable universe, the part we could in principle travel to, even at light speed, is far, far smaller. If we launched a beam of light, or set out ourselves at light speed, today, it could only ever reach galaxies that currently sit within roughly 16 to 18 billion light-years of us. Everything beyond that is already lost to us forever. We can see those distant galaxies. We can study them, photograph them, measure their light, analyze the elements they're made of. But we can never go there, and nothing we ever send could possibly arrive because the expansion of space will always outpace us. The light leaving us right now, heading toward them, will travel for eternity and never catch up. This is worth pausing on, because it overturns something we instinctively believe to be true. We tend to assume that if we can see something, we could, given enough time and enough speed, eventually get to it. That has been true for every explorer in all of human history. If you can see the mountain, you can climb it. If you can see the far shore across the water, you can build a boat and sail to it. If you can see a star, you might dream of one day reaching it, however long it takes. But the universe breaks that ancient rule. There are countless galaxies we can see with our telescopes, glittering across the dark, that are not merely far away, but fundamentally, mathematically unreachable. Seeing them is the most contact we will ever have with them. Their light is a message from a place we can never visit, sent across a gulf that is widening faster than light can cross it. So even at the ultimate speed, the great majority of the universe is closed to us. The numbers are stark. Of all the galaxies in the observable universe, only a small fraction lie within our reachable horizon. The vast majority, well over 90% of them, are already beyond any possible journey, beyond any message, beyond any reach. We were born too late, in a universe too spread out, expanding too quickly, to ever reach most of what we can see. There is one small piece of good news folded into all this, though it comes with its own quiet sorrow. Not everything is flying apart from us. Within our own local group, gravity is stronger than the expansion of space. The Milky Way, Andromeda, and the dozens of smaller galaxies bound together with them are held by their mutual gravity tightly enough that the stretching of space cannot pull them away from one another. These galaxies will stay together. In fact, as we've seen, the Milky Way and Andromeda are drawing closer, destined to merge. So this little cluster, this local group, is our true and permanent cosmic home. It is the one region that will not recede beyond our horizon, the one collection of galaxies that will remain reachable, in principle, no matter how the rest of the universe rushes away. Everything bound to us by gravity stays. Everything beyond that boundary leaves. And that draws the real map of what could ever be ours. Not the 2 trillion galaxies of the observable universe. Not even the thousands of galaxies of our supercluster. Just this one small group, this handful of galaxies clinging together against the expansion, destined eventually to fold into a single great galaxy that will be the entire universe, as far as any future inhabitant could ever travel or even see. It's a strange thing to hold in your mind. The cosmos is unimaginably vast, filled with trillions of galaxies. And the part of it that is truly, permanently, ours is a tiny island, soon to become a single merged galaxy adrift in an ever emptier sea. Everything else, however brightly it shines in our sky tonight, is already on its way out the door. There's one more layer of distance worth understanding, because it's the oldest light there is. When we look out into space, we look back in time. The farther we look, the further back we see. Look at the sun, and you see it as it was 8 minutes ago. Look at Andromeda, and you see it as it was 2.5 million years ago. Look at the most distant galaxies our greatest telescopes can find, and you see them as they were more than 13 billion years in the past. Glowing infant galaxies forming in the young universe. And if you look back, as far as it is physically possible to look, you reach a wall. Not a wall of matter, but a wall of light. For the first few 100,000 years after the universe began, it was so hot and dense that it was filled with a glowing fog. Light could not travel freely. It bounced endlessly between particles, trapped, unable to cross even a short distance. Then the universe cooled enough for that fog to clear, and in a single cosmic moment, light was set free to travel across space. That ancient light is still arriving today, stretched by billions of years of cosmic expansion into a faint glow that fills the entire sky. We call it the cosmic microwave background, and it is the oldest light in existence, a baby picture of the universe from when it was just a few 100,000 years old. It is, in a real sense, the edge of what we can ever see. We cannot see past it, because there was no free light before it. That glow surrounds us in every direction, the farthest and most ancient thing detectable, a faint warmth left over from the dawn of everything. And it, too, is part of the universe that is forever beyond our reach. We can detect it. We can map it in exquisite detail. We can read in its tiny ripples the seeds from which all the galaxies grew. But the place it came from has long since rushed away beyond our horizon, carried off by the same relentless expansion. We are reading a letter from a sender we can never meet. And it gets lonelier still, because the expansion is speeding up. For most of cosmic history, the expansion of the universe was actually slowing down, held back by the gravity of all the matter pulling inward. But a few billion years ago, something shifted. The expansion began to accelerate. A mysterious property of space itself, which scientists call dark energy, is pushing the universe apart faster and faster. We don't fully understand what dark energy is. It is one of the deepest unsolved mysteries in all of science. We only know that it dominates the universe, making up roughly 68% of everything that exists, and that its effect is to drive galaxies apart at an ever-increasing rate. As long as dark energy keeps doing what it's doing, the reachable universe will keep shrinking. Galaxies that are within our grasp today will, in the far future, slip beyond the horizon, one by one. Over billions of years, the galaxies outside our own little group will accelerate away, their light stretching and dimming and reddening, until finally it fades from view entirely. There will come a time, in the deep future, when the night sky of any creatures living in our region of space will hold only the stars of our own merged galaxy. Everything beyond, all the other galaxies, all the rest of the visible universe, will have receded so far and so fast that their light can no longer reach this place at all. To those distant future observers, the universe will appear to be a single island of stars, surrounded by infinite, empty blackness. They will have no way of knowing that the cosmos was ever filled with 2 trillion other galaxies. The evidence will have vanished, carried beyond the horizon by the expansion of space. The cosmic microwave background will have stretched away into undetectable faintness. The distant galaxies will have disappeared. Future astronomers, looking out with the finest instruments they could ever build, would conclude that their galaxy was the entire universe, alone in an endless void. And they would be wrong, through no fault of their own, simply because they were born too late to see the truth. This means something startling about right now. We are living in a golden age of cosmic visibility. We can still see the larger universe. We still have the evidence written across our sky, the distant galaxies, the ancient glow, the whole grand structure of the cosmic web. There is a window open, and it will not stay open forever. In the long story of the universe, the era when intelligent beings can look out and actually see how vast and full the cosmos truly is, may be a brief one, and we happen to be alive during it. The universe is not only too big to cross. In the deepest sense, it is also slowly disappearing. And if we follow that disappearance all the way to its end, the far future of the universe is a quiet and humbling thing to contemplate. Right now, we live in what astronomers call the stelliferous era, the age of stars, when galaxies blaze with light and new suns are constantly being born. But this era will not last forever. Star formation is already slowing across the cosmos. The clouds of gas that make new stars are gradually being used up. Trillions of years from now, the last new stars will form, and after that, no more. The existing stars will live out their lives and fade, one by one. The small, dim red dwarf stars, which burn slowly and frugally, will be the last to go, glowing faintly for trillions of years after the brighter stars have died away. And then, eventually, even they will dim into darkness. The galaxies will not be lit by starlight anymore. They'll be filled with the cold remnants of dead stars, faint embers drifting in the black. Over timescales so long, they make the current age of the universe look like an instant. Even those remnants will scatter and decay. The universe will spread out, cool down, and grow ever emptier and darker. This long, cold future is sometimes called the heat death, the final state of a cosmos that has expanded and cooled until almost nothing happens anywhere, ever again. It's not a violent end. There's no great collision, no final explosion, just a slow, gentle fading into cold and dark and silence, across spans of time the human mind cannot hold. I share this not to leave you in gloom, but to sharpen the point of tonight. The window in which the universe is bright, full, and visible is not infinite. We exist in the early morning of the cosmos, when the stars still shine and the galaxies still fill the sky. This is the time when looking outward reveals wonder, when the evidence of the larger universe is still there to be read. We didn't choose to be born now rather than in the long dark to come. But we are extraordinarily fortunate that we were, because now is when there's still so much to see. Let's step back from the numbers for a moment and think about what kind of journey we were ever really proposing. Even if expansion weren't in the way, even for the galaxies we could in principle reach, consider what travel at near light speed would actually involve. Space is not perfectly empty. It's threaded with thin gas and fine dust, individual atoms and tiny grains scattered across the void. At everyday speeds, these are nothing. But strike them at nearly the speed of light, and even a single speck of dust carries the energy of a bomb. A ship racing through the galaxy at relativistic speed would be sandblasted by the thin matter of interstellar space, every stray atom transformed into a burst of radiation. To survive, it would need shielding beyond anything we can currently imagine. And the energy to accelerate a ship to such speeds, then slow it down again at the far end, is staggering, far beyond the entire output of our civilization for thousands of years. These are the obstacles even before we reach the true wall of cosmic expansion. Some have dreamed of another approach entirely. Not fast ships, but slow ones. Vast vessels that would carry whole communities across the stars over thousands of years, with generation after generation living and passing on inside them, until the distant descendants of the original crew finally arrived. But even these generation ships, traveling far below light speed, run into the same fundamental truth. The galaxy is 100,000 light-years across. The reachable universe is billions of light-years wide. No amount of patience, no number of generations can cross distances that even light cannot cross in the time available. Every path leads back to the same conclusion. The universe was built on a scale that defeats not just our machines, but the very fastest thing those machines could ever hope to become. At this point, a hopeful voice usually speaks up. What about the exotic ideas? What about bending space itself, folding it, tearing a shortcut through it. Science fiction is full of warp drives and wormholes, ways of getting from here to there without crawling across the distance in between. And these ideas aren't entirely fantasy. The mathematics of relativity does, in principle, allow for strange possibilities. A warp drive would work not by moving a ship through space faster than light, which is forbidden, but by compressing space in front of the ship and expanding it behind, letting the ship ride a bubble of warped space toward its destination. A wormhole would be a tunnel connecting two distant points, a shortcut that bypasses the long road between them entirely. On paper, in the equations, these things can be written down. But the moment you ask what they would actually require, the dream collapses. A warp bubble would demand a form of matter with negative energy, something we have never found and may not exist in any usable form, in quantities that stagger the imagination. A wormhole would need similar exotic material just to hold itself open against its own tendency to collapse instantly. And even if you built one, there's no known way to place its far end somewhere useful. These are not engineering challenges waiting for a clever solution. They sit at the very edge of what the laws of physics might permit, and possibly beyond it. And it's worth pausing on just how far our real propulsion sits from even the gentlest version of these dreams. The fastest object we have ever built, the Parker Solar Probe, reaches a blistering 430,000 miles per hour as it whips around the sun. That sounds enormous, and by every human standard it is. But light moves more than 1,500 times faster still. At the probe's top speed, the journey to even the nearest star would stretch across roughly 7,000 years, longer than all of recorded human history laid end to end. Chemical rockets, ion drives, gravity assists, every trick we currently possess, all of them combined, still leave us crawling. The gap between what we can do and what we would need to do is not a gap we can close with patience or cleverness alone. It is a chasm written into the structure of speed itself. And here's the part that matters most for tonight. Even if every one of these exotic dreams came true, even if we could fold space and open tunnels at will, the expansion of the universe would still hold most of the cosmos beyond our reach. Because the regions that are receding faster than light are not just far away in ordinary terms. They are being carried off by the growth of space itself, and they keep accelerating away. The shortcuts of science fiction, even granted to us in full, would let us explore our own cosmic neighborhood more easily. But the great bulk of the universe, the overwhelming majority of those 2 trillion galaxies, would remain forever sealed away. There is no clever trick, no exotic loophole, no imagined technology that escapes this. The horizon is not a limit of our machines. It is a limit of reality. And it isn't only travel that the distances defeat. It's conversation, too. Suppose, somewhere out there, another civilization exists, looking up at their own sky, wondering the same things we wonder. The galaxy is so vast that even a simple greeting becomes almost meaningless. Send a radio signal, traveling at the speed of light, toward a star 1,000 light-years away, and your message arrives 1,000 years later. If they answer immediately, their reply reaches you 1,000 years after that. A single exchange, just a hello and a hello back, takes 2,000 years. Whole civilizations could rise and fall in the silence between question and answer. Reach out toward Andromeda, and a single round trip of greetings would take 5 million years. There is no holding a conversation across these gulfs. There is no back and forth, no dialogue, no relationship. At best, there could be messages flung into the dark, like notes sealed in bottles and thrown into an ocean so wide that no reply could ever return within the lifetime of anyone who sent them. The same wall that stops our ships also stops our words. Light speed is the fastest a message can travel, and against the scale of the cosmos, even our fastest possible message moves at the pace of geology. If the universe is full of voices, we may never be able to truly speak with any of them. We are each marooned on our own island of stars, able to shout across the void, but never to hear an answer come back in time to matter. And there's a quiet, humbling truth folded into this that's easy to miss. We have, in fact, already been broadcasting. For about a century now, ever since we began filling the air with radio and television and radar, our signals have been leaking off the planet and spreading outward into space at the speed of light. Every broadcast we've ever made is out there, racing away from Earth in an ever-growing bubble. But think about how small that bubble really is. A century of travel means our earliest signals have reached only about 100 light-years out in every direction. Set that against a galaxy 100,000 light-years across, and our entire radio bubble is a vanishingly tiny dot, a sphere so small that on any honest map of the Milky Way, it would be invisible. And those signals don't stay strong as they spread. They thin out, weaken, and fade into the background, hiss of the cosmos, so that even a civilization just a few dozen light-years away might struggle to pick our chatter out of the noise. We have been calling out, in a sense, for 100 years. But our voice is faint, and it has barely begun to cross the room. In the other direction, we have been listening, too. For decades, astronomers have aimed radio telescopes at the sky, scanning patiently across the frequencies, hoping to catch some signal that could only come from another mind. So far, the cosmos has answered with silence. That silence might mean we are alone, or it might simply mean that the distances are so vast and the windows of time so narrow that two civilizations almost never get to overhear each other before one of them is gone. A signal might have passed through our skies long before we had any instrument to catch it, or might arrive long after we're no longer here to listen. It's a sobering thought that the galaxy could have been full of conversations across its long history, rising and fading in different corners at different times, with no two voices ever quite overlapping in the same narrow window. The same wall of distance and light speed that keeps us from traveling also makes the simple act of finding each other almost impossibly hard. And yet, look at how far our sight can reach, even when our ships and our voices cannot. There's a famous experiment that captures this perfectly. Astronomers once pointed a powerful telescope at a tiny patch of sky that looked completely empty, a speck of darkness no bigger than a grain of sand held at arm's length. There seemed to be nothing there at all. They left the telescope, staring at that empty spot, gathering the faintest trickle of light for days on end. And when the image finally developed, that little patch of apparent nothingness was crowded with galaxies. Thousands of them. Spirals and ellipticals and strange young shapes scattered across the frame, each one a city of billions of stars. And all of it hiding in a sliver of sky that looked utterly black to the eye. That single image told us that the entire sky, in every direction, is packed with galaxies, layer upon layer, receding into the depths. Wherever we point, however empty it seems, the universe is full. Our newest telescopes have pushed this even further, catching light from galaxies so distant that it has been traveling for more than 13 billion years, leaving them when the universe was young and the first galaxies were only just taking shape. we are seeing the cosmic dawn, the earliest structures lighting up in the infant universe, their light arriving only now, after a journey that began before the Earth, before the Sun, before nearly everything. And there's something quietly staggering about being able to gather that light at all. These are not nearby objects, shining brightly into our telescopes. They are unimaginably faint. Their light spread thin by billions of years of travel and stretched out by the expansion of space until it has slipped almost entirely out of the colors our eyes could ever see. To capture them, our instruments have to sit perfectly still and stare at a single dark spot for hours, sometimes for days, patiently collecting one feeble photon at a time until a picture slowly emerges from the black. We are, in effect, catching individual scraps of light that left their galaxies before our planet existed, sorting them out from the darkness, and assembling them into a portrait of the universe as a newborn. We can never visit these places, but in a strange way, we don't have to, because the universe is constantly mailing its own history to us, written in light, and we have finally built eyes patient enough to read it. The picture it sends back shows a cosmos still in its first chapters, before galaxies had settled into graceful spirals, when everything was young and raw and forming. We cannot go to these places. We can never go to these places. But we can see them. From the surface of one small planet, we have built eyes that can catch light from the beginning of galaxies, across a distance and a span of time that our bodies could never cross in 1 trillion lifetimes. That is the consolation hidden inside tonight's hard truth. The universe will not let us travel to most of itself, but it does let us look. And looking, it turns out, can take us almost anywhere. It's worth being honest, then, about how far we have actually reached, in body rather than in sight. The farthest our hands have ever extended into the cosmos is carried by a few spacecraft now drifting beyond the planets. Aboard the Voyager probes, launched in the late 1970s, we placed golden records, etched with sounds and images of Earth. The voices of people greeting the cosmos in many languages. Music from across our cultures. The cry of a baby, the sound of rain, the rhythm of a heartbeat, a map showing where in the galaxy we live. It was a message in a bottle, flung into the cosmic ocean, on the slim hope that someday, somewhere, something might find it. Those records are now the most distant human-made objects in existence, traveling outward at tens of thousands of miles per hour. And yet, after almost half a century of flight, they have only just left the sun's immediate domain. They will not pass near another star for tens of thousands of years, and even then, only by chance, drifting silently through the dark. This is the true measure of our physical reach. A handful of probes, a few golden records, easing out into the nearest fringe of interstellar space across many decades, carrying a quiet hello that may never be heard. That is how far we have actually gone. And set against a galaxy 100,000 light-years wide and a universe of 2 trillion galaxies, it is the smallest of first steps, barely a toe dipped at the very edge of the shore. But it is a step. We, who cannot cross these distances, who may never send a living person beyond our own star, still reached out. We still wrote our message and cast it into the dark. There's something deeply human in that gesture. Knowing the odds, knowing the distances, knowing that no answer could ever return in time to reach us, we sent a piece of ourselves outward anyway, simply to say that we were here. And there's a strange kind of immortality in that gesture. Those golden records were built to last. Out in the deep cold of interstellar space, far from the weathering of wind and water, Far from the heat of any sun, there is almost nothing to wear them down. No rain to corrode them, no oceans to swallow them, no shifting continents to bury them. A gentle rain of cosmic dust will scratch at them over the ages, but slowly, so slowly that the records could survive largely intact for hundreds of millions of years, perhaps even longer. Think about what that means. Long after the last human structures on Earth have crumbled to dust, long after the continents have rearranged themselves into shapes we would not recognize, long after our cities and monuments are gone without a trace, those small golden disks will still be out there, drifting silently between the stars, still carrying the sound of a heartbeat and the image of a world. They may well outlast the Earth itself. Billions of years from now, when our aging sun swells into a red giant and scorches the inner planets, when the oceans boil away and the surface of our world is transformed beyond all memory, the Voyager probes will be far away in the dark, untouched, still carrying their quiet message. In a very real sense, those records may be the most enduring thing our species has ever made. A fragment of humanity that could persist almost unchanged for longer than the planet that made it. We could not cross the distances ourselves. But we found a way to send something of who we are into that vast dark, and to let it endure there, patiently, for an almost unimaginable stretch of time. So let's gather all of this together, because it reshapes how we should think about our place in everything. We started tonight with a dream of triumph. We imagined a ship moving at the ultimate speed, and for a brief, glorious afternoon, it crossed the solar system and made the planets feel small. But each step outward stripped away the illusion, one layer at a time. A single nearby star, 4 years away, and even that the very closest one. A familiar star you can point to in the sky, centuries away. Our own galaxy, 100,000 years just to cross, 25,000 merely to reach its glowing heart. The nearest large galaxy, 2.5 million years away, its light older than our species. Our home supercluster, hundreds of millions of years across at the speed of light. And the observable universe, tens of billions of light-years wide, holding 2 trillion galaxies, with the overwhelming majority of them not merely distant but permanently sealed off, receding faster than light through the swelling of space itself, slipping beyond a horizon that no ship and no beam of light will ever cross. At every single scale, the fastest speed the universe allows turned out to be not nearly enough. This is not a failure of our technology. This is not something a better engine or a cleverer fuel could ever fix. It is built into the very structure of reality. The speed limit of light and the expansion of space, working together, draw a boundary around what any being, anywhere, in any era, could ever reach. The cosmos is arranged so that even its ultimate speed is dwarfed by its own immensity. And there's something almost paradoxical hidden in that. Light is unimaginably fast. It crosses our entire solar system in a single afternoon. It laps the Earth 7 times in a heartbeat. And yet, set against the universe, light crawls. A beam of light leaving the most distant reachable galaxy today would spend more time in transit than the stars themselves have left to shine. The very thing that defines the maximum, the absolute fastest motion that can exist, becomes, on the cosmic stage, a symbol of just how vast everything else truly is. It's worth asking what we should feel about all this, because the honest answer isn't simply despair. Yes, there is a melancholy here, and it would be dishonest to pretend otherwise. We are bound, in a real and physical sense, to a small region of an enormous cosmos. Most of the universe we can see, we can never touch. And in the deep future, even the sight of it will be quietly taken away, fading galaxy by galaxy into the dark. That's a kind of loneliness written directly into the laws of nature, and there's no engineering our way around it. But look, just look, at what we've done from our small corner. We are creatures confined to a single, ordinary planet, orbiting an ordinary star in an unremarkable spiral arm of one galaxy among trillions. We have never sent a single person beyond our own moon. Our fastest probes, after almost 50 years of flight, have only just brushed the very edge of the sun's influence, and they would need 70,000 years to reach the nearest star. We are, by any honest measure, hopelessly local. And yet, from this tiny vantage point, sitting on the surface of one small world, we figured all of this out. We measured the speed of light to a fraction of a mile per second, starting from a clever observation about the timing of one of Jupiter's moons. We worked out the distances to the stars using the slight wobble of their positions across the seasons. We discovered that space itself is expanding by carefully reading the colors of distant galaxies. We found the oldest light in the universe, still glowing faintly across the entire sky. We calculated the size of the observable universe, the existence of the cosmic horizon, the acceleration driven by dark energy, the eventual fate of the cosmos, all without ever leaving home. We are small enough that the universe will forever keep most of itself beyond our reach. But we are clever enough to have mapped that universe anyway, to have understood our own limits, to have grasped the full shape of the place we live, even the parts we can never visit. There is a strange grandeur in that. To be a creature that cannot go to the far galaxies, yet can know with certainty that they are there. To be bound to one small world, yet able to hold the entire cosmos inside a single mind. We cannot cross the gulf, but we can comprehend it. And comprehension, in its own quiet way, is a kind of travel. When you truly understand what a galaxy 2.5 million light-years away is, when you grasp that its light has crossed an unimaginable void to land softly on your eye tonight, you have, in a sense, reached out and touched it. Not with a ship, with your mind. And no expansion of space can ever take that away. So, let me bring this all the way back to where we began. We imagined that we could travel at the speed of light, the fastest anything can ever move, the hard ceiling of reality itself. And we found that it still isn't enough. It's enough to cross our solar system in an afternoon, and that, on its own, feels like a miracle. But it takes years to reach the nearest star, centuries to reach the familiar ones, and 100,000 years just to cross our own galaxy. It would take millions of years to reach the next great galaxy, hundreds of millions to span our home supercluster, and even at that ultimate speed, the majority of the visible universe is fleeing from us faster than we could ever hope to chase it, lost behind a horizon that no ship and no beam of light will ever cross. The universe is not merely big. It is big in a way that defeats the very concept of speed. It is built on a scale so far beyond us that the fastest thing in existence might as well be standing perfectly still. And maybe that's the real lesson hidden inside tonight's impossible journey. The point was never to actually reach the edge of everything. We were never going to do that, not with light speed, not with anything that could ever be built or imagined. The point is what we become while trying to understand the attempt. We are tiny. We are slow. We are confined to a single pale world, adrift in an ocean we can never fully cross. But we look up anyway. We measure, we calculate, we wonder. We reach out with the only instrument that can truly cross these distances, which is the human mind. We hold the unreachable in our imagination and let it change us, let it humble us, let it fill us with something far better than disappointment. The cosmos keeps almost all of itself just beyond our reach, forever. And still, from this one small planet, we have learned to see it, to understand it, and to marvel at it. That, in the end, is enough. It has to be. Because it's all we have, and it's far more than we ever had any right to expect. So the next time you stand beneath a clear night sky and find that faint smudge of Andromeda, remember what you saw tonight. You are looking at light that left a galaxy 2.5 million years ago. You are seeing across a gulf that the fastest ship imaginable could never cross. And you, a small and slow and short-lived being, are understanding it perfectly well. We can travel at light speed in our minds, even when our bodies never will. And in that single act of understanding, the universe, vast and unreachable as it is, becomes, for one quiet moment, entirely yours. Thank you for joining me on this journey to the edge of what's possible and far beyond it. If this gave you a new way of looking up at the stars, a like or subscribe would mean a great deal, and it helps these explorations reach more curious minds like yours. Good night, and may you never look at the speed of light the same way again.